Okay, we're back with our solution chapter, chapter 12, and we are going to quantitatively express the concentration of a solution. And we're going to do it in several different ways. We want to talk about how much solute is dissolved in a particular solvent to make our solution. Of course, the more concentrated it is, the higher the value of that solution concentration will be. So, one way to measure solution concentration quantitatively is by using something called weight percent. This is probably the easiest calculation that we'll do in this section. Weight percent is simply the mass of the solute divided by the mass of the solution. Now, of course, we'll multiply that by 100 to make that a percentage. So, let's take a look at example number 1. We'll just do it quickly. If we have 15 grams of copper 2 sulfate and it's dissolved in 150 grams of water, what would be the weight percent of my solute copper 2 sulfate? Well, we're going to take the mass of our solute, 15.0 grams of CuSO4, and we're going to divide that by the mass of our solution. Now, some students that will be doing this quickly will say, okay, I'll just divide it by 150 grams of water. Well, be careful. Remember, our solution contains both the solute and the solvent, which is my water. So the mass of my solution is not 150 grams, it's the sum of the two. So I'm going to divide this by 150 grams of water plus 15 grams of my copper 2 sulfate. Then we'll multiply that by 100 to make it a percentage. Looks like we're allowed 3 sig figs. Now I'm going to get my really cheap, abused calculator that my kids have used, you can tell, just to show you that you don't need to have an expensive calculator. So we're going to take 15 and we are going to divide it by the sum of 150 and 15, which is 165. And we'll multiply that by 100, round that off to 3 significant figures. I end up with 9.09%. So 9.09% of that solution by weight is my copper 2 sulfate. Okay? Pretty straightforward calculation. Now we can actually tweak that a little bit. We can say, okay, what if we have a 15% solution of sodium chloride? And that solution has a mass of 325 grams. How many grams of that would be sodium chloride? Well, let's think. Wouldn't we simply take 15% of the mass of the solution, which is 325 grams? So to take 15% of a number, we'll multiply it by 0.15. I'm putting a 0 there to give me my 3 sig figs, times 325 grams. And this will give me the mass of my solution, that is sodium chloride. So we'll pull out the cheap calculator again, 0.15 times 0.15 times 325, and we end up with 48.8 grams of that being sodium chloride. 48.8 grams of NaCl. Now, of course, the rest of that, 325 grams, would be my water. But 48.8 of that would be 15% of 325 grams. Okay, we all set with weight percent. Pretty straightforward. Okay, next up is mole fraction. And you're going to find that mole fraction is pretty similar to weight percent, except we convert everything into moles. So it takes a little bit more time. So we're going to take the moles of our component, now that's either the solute or the solvent, and we're going to divide it by the total moles of our solution. Now we won't multiply this by 100, we're going to keep it as a decimal or as a fraction. So let's find the mole fraction of a sodium chloride solution, of course dissolved in water, if we have 350 grams of sodium chloride dissolved in 1,000 grams of water. First, we need to convert everything into moles. So we're going to take our 350 grams of NaCl, and we will go from grams to moles of NaCl. And we will take our 1,000 grams of water, and we will go from grams to moles of water. remember, to find a mole fraction, we have to find the moles of the component we're after divided by the total moles of my solution. So everything has to be converted to moles. Now, the formula weight of sodium chloride would be the weight of a sodium and a chlorine. So sodium, 22.99, we're going to call that, well, we'll call it 22.99. Well, let's just call it 23.0 today. And my chlorine, 35.45. So, let's see, 23.0 plus my chlorine, 35.45. That will give us 58.45 grams per mole. So, 58.45. And of course, the formula weight of water is the weight of 2 hydrogens and an oxygen. Each hydrogen is 1.0. We're going to call it 1.01 grams per mole, and oxygen 15.999. We're going to call that 16.00. So the sum of the two hydrogens and an oxygen would give us 18.02. So we'll have moles of NaCl, and we'll have moles of our water. So let's do the math. 350 divided by 58.45. I'm only allowed 2 significant figures here the way this is written. I'm going to go 5.9, and I'm going to write a small 9 down here. I know that's not significant, but I'm going to carry it with me in my next calculation, and I'm going to remember just to round off to 2 significant figures when I'm finished. For my water, I have 1,000 grams divided by 18.02, and that gives me 55.49 moles of water. So, to find the mole fraction of my sodium chloride, I'll take the moles of the component I'm interested in, which is my sodium chloride, 5.9, and we're going to put a small 9 down there just to remember, just to include that in my calculation. And once again, I'll round off at the end to 2 sig figs, divided by the sum of the sodium chloride moles and water moles. So 5.9 plus 55.49 moles. So let's see what we get here. 5.99. We'll get the sum down at the bottom first. We'll add that to 55.49. So that gives us 61.48. And we'll take my 5.99 on top, divided by the 61.48, and we're going to round this off to 2 significant figures. So I end up with, I'm running out of room here, a mole fraction of 0.097, and that would be the mole fraction of my NaCl. Okay, so once again, to find mole fraction, we take the moles of the component we're interested in. In this case, it was my solute, NaCl, and we divide it by the total moles of my solution. That means my masses had to be converted to moles. Okay, now for the most important unit of concentration. This is the one that we use most of the time in the laboratory. When you look in the laboratory, you look at the wash bottles that have different solutions in them, you'll see the capital letter M written next to a number. And that capital letter M stands for molarity. Now, by definition, molarity is the number of moles of solute divided by the volume of the solution in liters. So moles per liter is the unit of molarity. So, let's find the molarity of a solution made by dissolving 82 grams of calcium nitrate in 500 milliliters of solution. So, we need to have moles of solute, and that's my calcium nitrate. So, 82.0 grams of CaNO3,2, and we are going to go from grams of calcium nitrate to moles of calcium nitrate. Put a 1 by mole, and let's find the mass quickly of calcium nitrate. We have a calcium atom, which is 40.08, and we'll add that to the mass of, looks like we have 2 nitrogen atoms. Each one is 14.01, so we're going to call that 28.02 for the mass of 2 of them, plus the mass of 6 oxygens, right? There's 6 oxygens here. Each oxygen is 16.00 times 6 will give me 96.00. So I end up with 164.10 grams per mole. Now I have my moles of solute. I have my numerator taken care of. Now I simply need to divide by the volume of my solution in liters. So I have 500 milliliters, which is 0.5000 liters. Notice that grams of calcium nitrate divide out, and I have moles of calcium nitrate per liter. That is my unit of molarity. Now we usually symbolize that with the capital letter M. But remember, the capital letter M has the units of moles of solute per liter of solution. So let's see what that turns out to be. 82.0 divided by 164.10 divided by 0.5000 gives me, boy, 0.999 molar solution. That's pretty doggone close to 1, isn't it? But we'll stick with our significant figures and call that 0.999. But to be honest with you, if you said 1.00, I don't think I would be too upset at all. So just as a recap, molarity is moles of solute, so we had to go from grams to moles, divided by liters of solution, so we had to go from milliliters to liters, and we ended up with our molarity. Okay, let's do a couple more molarity problems. This time, for example number 5, I want to know the grams of sodium iodide that are needed to make 500 milliliters of a 0.100 molar solution. That's interesting. If molarity is moles of solute divided by liters of solution, and I want to find grams of sodium iodide, which one of these would I solve for? Well, let's keep it simple. I'm given the molarity, and I'm given the volume. So I'll be solving for moles. And I understand that's not grams, but can't we convert moles of sodium iodide to grams? Of course we can. Now, I like to start with my volume of the solution in liters. So I'm going to say 0.5000 liters. And I'm going to hop out of liters and get into moles of sodium iodide. You'll notice I'm using the molarity, moles per liter, as a conversion factor. The molarity is 0.100 moles of sodium iodide per liter. So when you multiply volume in liters by the molarity, we get moles of solute. Then we simply need to go from moles of sodium iodide into grams of sodium iodide. 1 mole of sodium iodide, well, let's find its mass. Sodium, alright, we'll go with 22.99 this time. And iodine, looks like it's 126.90. So plus 126.90 gives me 149.89. 149.89. So, moles of sodium iodide are gone, and I have grams of sodium iodide, which is exactly what I want. So let's take a look. We'll take 0.5 times 0.1 times 149.89. Looks like my calculator says 7.4945. Looks like we're only allowed 3 sig figs, so we're going to go ahead and call this 7.49 grams of sodium iodide would be in that solution. Okay, let's do another molarity problem. Example number 6. This time I want to find volume of a 0.5 molar solution that can be made from 80 grams of sodium hydroxide. So molarity equals moles per liter. We're going to be solving for liters here. Now, when I do that, I like to start with grams of my solute. So I'm going to start with 80.0 grams of sodium hydroxide. We will go from grams of sodium hydroxide into moles of sodium hydroxide. So let's find the weight of that quickly. Sodium, we just saw, we're calling that 22.99. Oxygen, of course, we've seen that a lot, 16.00. And what else do we have? Hydrogen, that's 1.01. So we have 40.00 grams per mole. Well, that math looks pretty simple. I'm going to try this without a calculator. 80 divided by 40, that's going to give me 2. Well, let's continue on with our unit analysis. Let's not quite finish the calculation yet, because don't we have to get into liters? And if we stopped by taking 80 divided by 40, we would just have moles. So our last step is to go from moles of sodium hydroxide into liters of solution. And I'm going to use my molarity as a conversion factor again. Isn't that 0.500 moles per liter? So 0.500 moles per liter. So moles of sodium hydroxide are left out, or divided out, excuse me, and I'm left with liters. So we have 80 divided by 40, which is 2, divided by a half, which would give me 4.00 liters. Should we check the math just for fun? 80.00 divided by 40.00 divided by 0.500 gives me 4, and I have 3 significant figures, 0.00 liters. Okay, in the interest of time for this video, because we're already past 16 minutes, we're going to skip example 7, and we'll probably do that one in class, because I want to get to molality. And we'll stop right here. We'll finish up with dilution on another day. Maybe just a short addendum to this video. All right, molality is the last unit of concentration that we're going to worry about in this chapter. Sounds a lot like molarity, doesn't it? Molality has the same numerator, moles of solute. However, the denominator is different in 2 different ways. First of all, it's kilograms, not liters. And it's solvent, not solution. So molality is moles of solute divided by kilograms of just the solvent. Now, the symbol for molality is the small letter m. Remember molarity, we had capitalized the m. So, let's find the molality of a solution that has 15 grams of C2H5OH ethanol in 350 grams of water. So we're going to take our 15 grams of C2H5OH. We will go from grams of C2H5OH into moles of C2H5OH. Don't we want moles of solute on top? So what is the mass? Well, we have 2 carbons, so we'll pull out our periodic table again. Each carbon, 12.01. So 2 of them would be 24.02, plus a total of 6 hydrogens, 5 here and 1 more. Each one is 1.01, so 6 of them would be 6.06, plus we have 1 oxygen, which is 16.00. So we end up with a molecular weight of 46.08 grams per mole. So grams of ethanol are gone, and we have moles. Now we're going to divide that by kilograms of just the solvent. So I have 350 grams of water. That would be 0.3500 kilograms of water. So I will have moles and kilograms left, which is the unit I'm after for molality. So let's do the math. 15 divided by 46.08 divided by 0.3500. I'm allowed 3 significant figures. I have 0.930, and I'm going to symbolize that with the small letter m, which recall is moles per kilogram of solvent. Okay, one more problem for the day, and we'll wrap this up. This has gone much longer than I'd like it to normally, so thanks for sticking with me. But you did ask me to do more examples for you when it came to our quantitative work. So here we go. Example number 9. How many grams of acetic acid are needed to make a 0.50 molal solution in 750 grams of water? So I want grams of acetic acid. Now remember, molality is moles of solute divided by kilograms of solvent. I have kilograms of solvent, and I have the molality. So I'll be solving for moles of acetic acid and then converting that to grams. I like to start these problems with the mass of the solvent in kilograms. So 0.75, I'm going to put a decimal here, 0.750 kilograms of water. And then we're going to go from kilograms of solvent to moles of solute, which is my acetic acid, HC2H3O2. And according to this, I'm going to use my molality as a conversion factor. It's 0.50 moles per kilogram. So I've just used molality as a conversion factor. It allowed me to get out of kilograms and into moles of solute. My last step will be to simply convert moles of acetic acid into grams, because that's what I'm after. How many grams of acetic acid? So let's see what the molecular weight of acetic acid is. We have 4 hydrogens. Each one weighs 1.01, so that's 4.0 grams due from my hydrogens. 2 carbons. Each one's 12.01, so that's 24.02 from the carbons. And 2 oxygens, each one's 16.00, so that's 32 for my oxygens. That gives me 60.06 grams per mole. So moles of acetic acid are gone, and I'm in grams. So let's see what that turns out to be. 0.750 times 0.50 times 60.06. Looks like I'm only allowed 2 sig figs here, so we're going to call this 23 grams of HC2H3O2. Okay? Alright, I'm going to make a second video to this. I know this is going long, but I'm going to do some more example problems for you, if that's okay with you. And I'm also going to discuss a little bit of dilution, and we'll do a couple of dilution problems. I think you'll like this. It's sort of it's pretty easy. I think you'll enjoy doing that. And then we'll wrap up our solution concentration part of this chapter. So sorry this went a bit long. Hopefully you're able to understand this. It's pretty important stuff, and we'll go over it again in class. Thanks. Bye-bye.